Hello and welcome to Science Night Tales. I'm glad you have found this quiet moment to pause. Tonight, we are going to look beneath the surface. We often think of history as something written in books, but the Earth keeps its own record, pressed into stone, layer by layer over millions of years. We are going to explore a very thin, very strange line found in rocks all over the world. It is a boundary that marks the end of one world and the beginning of another. We will look at how a single day, 66 million years ago, changed everything, and how the planet quietly preserved the memory of that day in a layer of dust no thicker than your finger. You do not need to worry about ancient catastrophes tonight. The dust has settled, the world has recovered, you are safe. You can simply let the deep time wash over you. If this perspective helps you find peace in the permanence of the Earth, you are welcome to like or subscribe. For now, let go of the present and let's dig down into the past together. If you could cut straight down through the ground beneath your feet, past the roots and soil and stone, you would begin to see something like pages in a book. One layer resting on another. Thin bands of sand, thicker bands of limestone, darker seams of clay. Each one laid down slowly, quietly, over spans of time that stretch far beyond human memory. Most of these layers change gradually. Grain size shifts a little, color fades from one shade to the next. The story moves forward without sharp turns. A coastline becomes a shallow sea. A shallow sea becomes dry land, nothing sudden, nothing abrupt. Geologists are used to that kind of patience. They expect Earth's history to be written slowly, almost carefully, one deposit at a time. But then there is a line, not a thick layer, not a dramatic band of rubble, just a very thin boundary. Sometimes only a few centimeters, sometimes less. A narrow stripe that separates one world below from a different world above. Below it, the rock layers are crowded with fossils, shells, bones, traces of life that flourished for millions of years. Above it, many of those forms are simply gone, not reduced, not transformed, just absent. The boundary itself is sharp, clean, as if something changed all at once. Not over thousands of years, but in a moment that geological time still remembers. What makes this line more unusual is where it appears. It is not confined to one region. It is found in North America, in Europe, in Asia, in Africa. It lies beneath ancient seabeds and deep ocean floors. It appears on land and beneath water, across continents that were already far apart when the layer formed. Different environments, different climates, same line. When scientists first noticed it, there was nothing about it that looked dramatic. No towering structure, no obvious sign of violence, just a thin boundary that refused to blur. And inside that boundary, something else stood out, a chemical signal that did not fit. The element was iridium, a metal that most people never encounter. It is dense, chemically stable, rare. On Earth's surface, it is almost non-existent. It prefers to sink toward the planet's core, carried downward when Earth was still forming. In surface rocks, iridium is usually measured in trace amounts so small they barely register. A few parts per trillion, sometimes less. But in this thin boundary layer, the numbers changed, not slightly, sharply. In samples taken from Italy, iridium levels jumped far above normal. In Denmark, the same spike appeared. Later, in New Zealand, then in Spain, then in North America. Each site told the same quiet story. A sudden increase, a narrow window in time, and then a return to near zero above it. The pattern was consistent, too consistent. Different teams, different continents, different rock types. The same signal appeared, locked to the same moment in Earth's history. Iridium does not behave this way under normal conditions. It does not concentrate itself evenly across the globe. It does not appear all at once and then vanish. Earth's usual processes do not move elements with that kind of precision. Volcanoes can release metals, but their deposits are uneven. Rivers carry material, but they spread it locally. Plate tectonics reshapes continents, but it works slowly, unevenly, and with visible distortion. This layer showed none of that. It was thin, flat, widespread, and brief. If iridium had slowly accumulated, it would smear across many layers. If it came from local sources, it would cluster in certain regions. If it came from volcanic activity, it would leave behind other chemical signatures alongside it. But this boundary carried a single, clear signal: a spike. Then silence. The timing made it even more puzzling. Radiometric dating placed the layer at about 66 million years ago. Not a range, not a long interval, a narrow slice of time. The same age again and again, no matter where the sample came from. Below that line, ecosystems were complex and abundant. Above it, many familiar species were missing. Not gradually fading out, but stopping. The rocks themselves seemed to pause. This raised a question that could not be ignored. What process could spread a rare element across the entire planet, deposit it in a thin, uniform layer, and do so in a span of time short enough to appear instantaneous in the geological record? It could not be erosion. It could not be slow sedimentation. It could not be ordinary volcanic activity acting alone. Whatever caused this boundary had to act everywhere at once. It had to inject material into the atmosphere, not just onto land. It had to bypass oceans and mountains and continents as if they were not there, and it had to do it quickly. The rocks were not telling a story of gradual change. They were marking an interruption, a single event, brief, global, powerful enough to leave a chemical trace that would survive for tens of millions of years. The boundary itself remains quiet. It does not announce its presence. You can stand above it without knowing it is there. Forests grow above it. Cities rise above it. Oceans move above it. But once you know it exists, it becomes difficult to ignore. Because it suggests that Earth's history is not only shaped by slow forces acting patiently over time. Sometimes it is shaped by moments so sudden that they leave behind a line instead of a slope. A moment when material arrived from somewhere else, from beyond the systems that usually govern the planet's surface. And that realization leads to the next question. Not what the layer contains, but where it came from, and what kind of event could place it there. To understand what happened next, the focus has to move away from the ground and toward an object that was already on its way long before any layer formed. It was not small. Based on the size of the crater it left behind, scientists estimate the object measured about 6 miles across, roughly 10 kilometers from one edge to the other. That distance is difficult to picture in everyday terms, so it helps to stay with the numbers. An object of that diameter, composed mostly of rock and metal, would have carried a mass measured in trillions of tons, not spread out, not diluted, concentrated into a single moving body. Its density mattered. Rocky material does not compress easily. It does not slow down quickly. And when it moves at speed, it carries momentum that is difficult to interrupt. The asteroid was already traveling through space long before it encountered Earth. Like most objects in the solar system, it followed a stable path governed by gravity. When that path intersected Earth's orbit, the encounter became unavoidable. By the time it reached the upper atmosphere, its velocity was extraordinary. Estimates place its speed at more than 20 kilometers per second. That is over 40,000 miles per hour. At that speed, distance collapses. The time it takes to cross the entire atmosphere is measured in seconds. This velocity was not something the atmosphere could meaningfully resist. Earth's air feels substantial to living organisms. It slows falling objects. It creates friction. It burns meteors into brief streaks of light. But those effects depend on size and speed. Small objects heat up and disintegrate because they present a large surface area relative to their mass. They lose energy quickly. They fragment. This object was different. With a diameter of several miles, its surface area was small compared to its total mass. The outer layers did heat rapidly, but the energy absorbed was insignificant relative to the energy it carried. The atmosphere had no time to respond, no time to deflect it, no time to slow it down in any meaningful way. From the moment it encountered air molecules to the moment it struck the surface, only a few seconds passed. During that time, its speed remained almost unchanged. What mattered most was not just how fast it was moving, but how much energy that motion represented. Kinetic energy increases with mass and with the square of velocity. When both are large, the result is extreme. Calculations based on crater size and shock features suggest the energy released on impact was equivalent to tens of millions of megatons of TNT, often summarized as roughly 100 trillion tons of TNT. That number is not meant to be vivid. It is meant to be precise. It places the event far beyond any volcanic eruption, far beyond any earthquake, far beyond any human-made explosion. This energy was not released gradually. It was delivered in a single moment, concentrated at one point on Earth's surface. Before impact, the asteroid was a solid body. After impact, it no longer existed in that form. The object did not bounce. It did not break apart and scatter. It was vaporized. The rock and metal that made up the asteroid were instantly converted into high-temperature vapor and fine particles. So was a large volume of Earth's surface at the impact site. The mass of material involved increased rapidly as the asteroid's energy transferred to the crust. This transfer happened faster than rock could deform slowly. It happened faster than heat could dissipate. The result was an explosive release, driven not by chemistry but by physics. The speed of the incoming object is also why atmospheric friction played such a minor role in shaping the outcome. Friction requires time, it requires sustained contact, it requires gradual energy loss. Here, there was no gradual phase. The asteroid crossed the atmosphere so quickly that heating occurred only at the surface and only briefly. There was no opportunity for deceleration, no prolonged interaction. From a physical standpoint, the atmosphere was almost transparent. The object arrived at the surface with nearly all of its original velocity intact. This is why the impact energy was not spread out along a path. It was concentrated at a single location. The Earth did not experience a long warning. There was no extended period of atmospheric heating or slowing. There was simply the arrival. This helps explain why the consequences were global, even though the impact site was local. When energy of that magnitude is released suddenly, the effects do not remain confined. Shock waves propagate through solid rock. Material is ejected upward, not just outward. The boundary between surface and atmosphere briefly disappears. At the moment of impact, Earth's crust behaved less like a rigid shell and more like a fluid under extreme stress. But at this stage, it is important to stay with the object itself. Its size ensured survival through the atmosphere. Its mass ensured immense energy. Its velocity ensured that energy would be delivered almost instantaneously. Nothing about this required intention or direction, no adjustment, no targeting. It was the result of orbital mechanics, a path that intersected another path. The physical properties alone explain why the event unfolded the way it did. A smaller object would have burned up. A slower object would have delivered less energy. A less dense object might have fragmented earlier. This one did not. It arrived intact, it arrived fast, and it arrived carrying an amount of energy that Earth's surface was not structured to absorb gently. At this point in the story, nothing has yet spread around the world. Nothing has settled into layers. Nothing has cooled. There is only an object and a planet, and a moment when their interaction releases more energy than Earth had experienced in tens of millions of years. What happens next depends not on the object alone, but on how that energy moves through rock, water, and air once the impact occurs. The moment of impact did not unfold over minutes or even over seconds. It unfolded faster than human perception can track. When the asteroid reached the surface, its velocity had barely changed. There was no gentle contact, no gradual transfer. The rock at the impact site experienced forces far beyond its structural limits. Compression occurred instantly. The asteroid and the crust beneath it were subjected to pressures greater than those found deep inside the planet's mantle. Under those conditions, solid rock no longer behaves as a solid. It behaves as a compressible material. The first stage was contact. The second stage followed almost immediately. A transient cavity began to form. Rock did not crack in the usual way. It flowed outward under extreme stress. Material beneath the impact site was pushed downward and sideways at speeds measured in kilometers per second. This excavation phase lasted only moments. The asteroid itself did not remain intact. The temperatures generated at the point of contact exceeded several tens of thousands of degrees. At those temperatures, chemical structure becomes irrelevant. The asteroid's rock and metal were converted into vapor almost instantly. The same process affected a large volume of Earth's surface. Granite, sediment, water, all were exposed to the same sudden energy input. Material that had taken millions of years to settle into place was converted into a rapidly expanding mixture of gas and fine particles. The transient cavity grew larger than the final crater would be. Its walls were unstable. Gravity began to reassert itself almost immediately. As the cavity expanded, shock waves radiated outward. Through solid rock, these shock waves traveled faster than the speed of sound in air. They moved as intense pressure fronts, compressing and decompressing material in rapid succession. Mineral structures were altered, crystalline lattices were deformed, some minerals briefly entered phases that exist only under extreme pressure. These changes would later become part of the physical evidence preserved in surrounding rock formations. The shock did not remain confined to the crust, it passed into the oceans. At the time of impact, the site was covered by shallow seawater. The water did not cushion the event. It responded as any fluid would under sudden compression. It was displaced violently. Large volumes of water were forced upward and outward, contributing additional material to the expanding plume above the impact site. Meanwhile, the transient cavity began to collapse. Rock that had been forced outward and upward fell back inward under gravity. This collapse reshaped the cavity, forming a more stable, bowl-like structure. The process created a complex crater with a central uplift and concentric features formed by the rebound of compressed material. All of this happened quickly. The excavation and collapse phases together lasted only a few minutes. But the most far-reaching consequence was not the shape of the crater. It was the movement of material away from the impact site. The energy release did not remain localized. A plume of vaporized rock, metal, and water expanded upward at extreme speed. It pierced the atmosphere, carrying debris far beyond the lower layers of air. This material was not limited to large fragments. Much of it consisted of fine particles, dust-sized, smaller. The finer the particles, the longer they could remain suspended once they reached high altitudes. The plume rose beyond the stratosphere. Some material reached near space altitudes before gravity slowed its ascent. At that point, the direction of motion changed. Material that had been launched upward began to spread outward, not in a narrow column, across a widening area. As the plume expanded, it interacted with atmospheric circulation patterns. The particles were carried laterally, not just vertically. This marked the transition from a local event to a global one. At ground level near the impact site, the environment was radically altered. But above it, something more subtle and more persistent was beginning to take shape. The atmosphere was being loaded with material that did not belong there. Iridium-bearing particles were now mixed into this cloud. Material originating from the asteroid itself was distributed alongside vaporized crustal rock. Because the asteroid's material had been completely vaporized, its components were free to disperse widely. There were no large surviving fragments, no intact body remaining, only redistributed matter. Shockwaves continued to propagate outward through the planet's crust long after the plume had risen. They weakened with distance but remained measurable over vast areas. Seismic energy traveled through the Earth, leaving subtle signatures in rock layers far from the crater. In the oceans, pressure waves moved rapidly, disturbing water columns over large regions. But these effects were brief. The lasting consequence was atmospheric. Once the initial expansion slowed, gravity began its steady work. Material in the plume started to cool. Vapor condensed into fine particles. Larger fragments fell back to the surface relatively quickly, but the smallest particles remained aloft, carried by global circulation, unrestricted by continental boundaries. This was the material that would eventually settle out slowly, evenly across the planet. This was the material that would form a thin layer. At the moment of impact, none of that was visible from the surface. There was only heat, pressure, and motion. No warning, no gradual transition. Just the rapid conversion of kinetic energy into mechanical disruption, thermal energy, and atmospheric loading. The crater itself, though immense, was only one part of the process. The true reach of the impact extended upward into the layers of air where material could travel far beyond the site of origin. From this point forward, the consequences would no longer be defined by force alone. They would be shaped by how long fine particles could remain suspended, and how evenly they could spread before returning to the surface. After the force of the impact faded, after the shock waves weakened, after the crater began to settle into its final shape, the most important changes were no longer happening at the surface. They were happening above it, high in the atmosphere. The plume created by the impact did not behave like ordinary smoke or ash. It was composed of material that had been heated beyond normal limits, then rapidly cooled. As it rose and expanded, vapor condensed into particles of many different sizes. Some were large, pebble-sized fragments, sand-sized grains. Those fell back quickly, pulled down by gravity within hours or days. But much of the material was far smaller, microscopic particles, fine dust, aerosols measured in micrometers. These particles had very little mass individually. Their surface area was large compared to their weight. That made them slow to fall. Their composition varied. Some particles came from Earth's crust, pulverized rock, mineral fragments altered by extreme heat and pressure. The others came from the asteroid itself. That distinction mattered. The asteroid contained elements that are uncommon at Earth's surface. Iridium was one of them. Because the asteroid had been completely vaporized, its material did not remain clustered. Iridium-bearing particles were released into the plume alongside silicates and other debris. Once mixed into the atmosphere, these particles could not be separated easily. They moved together, responding to the same forces. At high altitudes, air behaves differently than it does near the surface. Density drops, turbulence changes, vertical mixing becomes slower. Particles that reached the stratosphere were no longer exposed to frequent rainfall. They were no longer swept out quickly by weather systems. Instead, they entered a region where residence times are long. Global circulation patterns took over. Winds at these altitudes move material laterally across vast distances. They do not follow the same paths as surface winds. They are shaped by Earth's rotation, temperature gradients, and large-scale atmospheric structure. Once particles were caught in these flows, they began to spread, not outward from the impact site in a single direction, but around the planet. Over weeks and months, material was transported across hemispheres, across oceans, across continents. This distribution did not require additional energy. It was passive. The atmosphere did the work. As particles circulated, collisions caused some to clump together. Others remained isolated. The smallest particles were the most persistent. Their settling velocities were extremely low. Gravity pulled on them continuously, but the force was slight. In the absence of frequent precipitation at those altitudes, there was nothing to accelerate their removal. This is why the material did not return to the surface quickly. It remained suspended, not all at the same height, not all at the same concentration, but enough of it persisted to alter the atmosphere's ability to transmit sunlight. The particles were effective at scattering and absorbing incoming radiation. They did not need to form a dense cloud. A thin, widespread haze was sufficient. This effect developed gradually. There was no instant darkness. As more material spread and settled into stable atmospheric layers, solar radiation reaching the surface declined. Temperatures began to drop. But in this phase of the story, the emphasis is still on movement and delay. The iridium-bearing particles followed the same paths as the rest of the dust. Because iridium is chemically stable, it did not react away. It remained bound within solid particles. As those particles circulated, iridium was carried with them. This is why the later geological record shows such uniformity. The atmosphere acted as a global distributor. It did not deposit material in thick piles. It allowed particles to settle slowly, evenly over time. Years passed before much of this fine material returned to the surface. During that time, the planet's surface experienced conditions very different from those before the impact. But the rocks would not record those conditions directly. They would record the end of the process, when gravity finally overcame suspension, when particles began to fall out of the atmosphere. They settled quietly. No explosion, no disturbance, just a gradual accumulation of fine material, layer by layer across land and sea. Because the particles were so small, they settled uniformly. They were not sorted by rivers or wind near the surface. They arrived from above. This is why the resulting layer is thin. This is why it is widespread. And this is why it is chemically distinct. Iridium arrived with the dust. It arrived everywhere, and it arrived within a narrow window of time. At the moment, nothing about this process would have been visible to an observer on the ground. The sky would have looked different, dimmer, muted, but the true significance lay in duration, not intensity. The atmosphere had become a reservoir, holding material aloft, delaying its return. This delay is what allowed consequences to unfold slowly, even though the initiating event had been sudden. And as the dust continued to circulate, as sunlight remained reduced, another set of effects was beginning to take shape below. Effects that would leave their own marks in the geological record. As the dust continued to circulate, as fine particles remained suspended high above the surface, the planet began to experience a different kind of interruption. Not one driven by force, but by absence. Sunlight did not stop reaching Earth all at once. There was no single moment of darkness. Instead, the reduction was gradual, layered, persistent. High in the atmosphere, aerosols and dust particles scattered incoming solar radiation. Some light was reflected back into space. Some was absorbed and converted into heat far above the surface. What remained was weaker, diffused, stripped of intensity. Days still followed nights. The sun still rose, but the quality of light changed. Shadows softened, contrast diminished. The sky took on a muted tone. This mattered more than it seemed. Earth's surface systems are tuned to small differences in energy. A few % reduction in incoming sunlight is enough to shift temperatures globally. As less radiation reached the ground, surface cooling began. Not immediately dramatic, not uniform. Oceans cooled slowly, storing heat from earlier conditions. Land cooled faster, responding quickly to reduced input. Seasonal patterns weakened. Summers became less warm, winters extended. In many regions, temperatures dropped below thresholds that ecosystems depended on. Plants were the first to feel the change. Photosynthesis is sensitive not only to light presence, but to light strength. When radiation falls below a certain level, energy capture declines sharply. Leaves still existed, chlorophyll still absorbed light, but the rate of energy production slowed, growth stalled. In some regions, it stopped entirely. This was not a sudden die-off, it was a failure to continue. Plants could survive for a time on stored energy. Seeds could remain dormant, roots could persist underground. But without sufficient sunlight, no new biomass could be produced. The base of the food chain weakened. Herbivores depended on steady plant growth, fresh leaves, new shoots. As plant productivity declined, Herbivores faced scarcity, not everywhere at once, not in the same way. Some ecosystems collapsed quickly, others resisted longer, but the direction was the same. Predators felt the effects later. At first, prey still existed. Stored fat and body mass delayed the impact, but as herbivore populations fell, predators followed. Food chains did not snap instantly. They unraveled, link by link. The oceans were not immune. Phytoplankton rely on sunlight near the surface. When light penetration decreased, their productivity dropped. This reduced the food supply for zooplankton, which fed small fish, which supported larger predators. Marine ecosystems, often buffered by water's thermal stability, began to thin from the bottom upward. Temperature decline reinforced the problem. Cooler conditions slowed metabolism. Growth rates decreased. Reproductive cycles lengthened or failed. Species adapted to stable climates struggled as variability increased. Frost appeared in regions where it had once been rare. Growing seasons shortened. Ice did not need to cover the planet to be disruptive. It only needed to appear more often and linger longer. The interruption of sunlight was not dramatic to the senses. There were no constant storms, no visible catastrophe day after day. Instead, there was persistence, a dimming that did not lift, a cooling that did not reverse. Year followed year with insufficient recovery. This is what made the event so effective. Life is resilient to shocks. It is far less resilient to prolonged constraint. Energy flow through ecosystems slowed, then narrowed, then failed to sustain complexity. Simpler organisms survived more easily. Those with flexible metabolisms, those able to endure long periods of low activity. Highly specialized species struggled. Large bodies required more energy. Complex food webs required stability. Both became liabilities. By the time dust finally began to settle out of the atmosphere, by the time sunlight slowly strengthened, many systems were already gone. The interruption had lasted long enough to reshape the biosphere. What followed was not immediate recovery. It was a long interval of adjustment, dominated by survival rather than growth. The sun had never stopped shining, but for a time, it had stopped sustaining the world it once supported. And the consequences of that pause would echo far beyond the darkness itself. The atmosphere did not clear all at once. There was no final moment where the sky suddenly returned to blue. Instead, it thinned, slowly, almost politely. Fine particles that had spent years suspended in the upper air began to lose their balance. Not falling yet, just drifting a little lower, entering denser layers, meeting more resistance, losing energy. Gravity did the rest, not violently, not dramatically, just steadily. Microscopic dust grains descended through the atmosphere. Aerosols followed gentle, irregular paths downward. Tiny fragments of vaporized rock, metal, and mineral, once part of a solid asteroid, made their way back to the surface. This was not weather in the usual sense. There were no storms strong enough to rearrange continents, no seasonal cycles restoring familiar patterns. What was happening now was quieter than that. Particles settled through still air and thin clouds. They landed on oceans, lakes, floodplains, forests that no longer looked like forests. They sank through water columns. They rested on seabeds already stripped of much life, and they did this everywhere. The same slow descent occurred across the planet, north and south, east and west, land and sea. This is what gives the layer its strange consistency. As the dust reached the surface, it did not pile up into thick deposits. Each particle was too small, too widely dispersed. The supply was finite, released in a short window of time, so the layer grew thin, very thin. In many places, it measures only a few centimeters, in some, just a few millimeters. Barely visible to the eye unless you know exactly where to look. Yet despite this thinness, it is continuous. Geologists find it in rock outcrops separated by oceans, in deep-sea cores drilled thousands of meters below the surface, in sediments laid down in environments that once had nothing in common. Different climates, different ecosystems, different geological settings. The layer is still there, and it is sharply defined. Normally, Earth does not preserve such clean boundaries. The surface is almost always being disturbed. Roots push downward, animals burrow, microorganisms churn sediments, water moves material back and forth, layers blur into one another. Time smears the record. But during this interval, many of those processes were weakened or absent. Plant life had declined dramatically. Large forests no longer stabilized soils. Root systems that once broke and mixed layers were gone or reduced. Animal activity was diminished. Many burrowing species had disappeared. Others survived only in limited regions, their populations too small to significantly disturb sediments. Even in the oceans, mixing changed. With food chains disrupted, biological activity near the seafloor declined. Sediments settled and stayed where they landed. The planet, in a sense, became still. Not frozen, not lifeless, but quieter. That quiet mattered, because it allowed the dust to settle without being erased. Grain by grain, the boundary layer formed. It did not form everywhere in exactly the same way. Some regions received slightly more material, others slightly less. Local conditions still mattered, but the overall result was the same. A thin band, chemically distinct, globally synchronized. Iridium was locked into this layer. An element that rarely appears in surface rocks suddenly appeared at concentrations dozens to hundreds of times higher than normal background levels, and it appeared at the same relative position in the geological column. Below the layer, rocks tell one story. Above it, another. The boundary is sharp because it represents a short interval of time. In geological terms, almost instantaneous. There was no long transition where iridium slowly increased and then slowly faded. There was a spike, a peak, and then a return to normal. That pattern matters. It tells geologists that the source was sudden, external, global, and once the layer formed, it stayed intact. Later, sediments accumulated above it. Rivers shifted, seas advanced and retreated, continents drifted. But the boundary remained, sometimes compressed by pressure, sometimes tilted or fractured by tectonic forces, still recognizable, a quiet line running through stone. When geologists split rock samples today, they often pause at this boundary, not because it looks dramatic, but because it feels deliberate, as if the planet marked the moment. Below the line, fossils are abundant, diverse, complex. Large organisms appear regularly. Ecosystems seem stable. Above the line, things change. Species are fewer. Body sizes shrink. Entire groups vanish. The boundary layer itself contains almost no fossils. It is a pause, a thin interval where deposition continued but life did not fully participate. That absence is part of the evidence. The layer does not explain extinction by itself. It does not show which species survived or how recovery began. But it sets the stage. It provides the timestamp. It tells us when to look and where. Everything that follows in the fossil record is interpreted in relation to this line. It divides before and after, not as a metaphor, as a physical reality. A few millimeters of dust settled quietly and preserved long enough to guide an entire scientific reconstruction of Earth's past. What comes next is written above this boundary, in shells that suddenly disappear, in bones that never reappear, in the slow return of life, altered and reshaped. The line does not end the story. It tells us exactly where the story changes. Below the boundary, the fossil record is full. Layer after layer contains variety. Many forms, many sizes, many strategies for survival. Bones appear regularly. Shells are dense. Teeth, tracks, nests, fragments of ecosystems captured in stone. It is not a perfect record. It never is. But it is rich. Species appear, persist, change slowly, then fade. New ones replace them. Patterns repeat across regions. On land and in the oceans, life is active and structured. Then the line appears, and above it, the record changes immediately. Not gradually, not unevenly, immediately. In the layers just above the boundary, the number of species drops sharply. The diversity that once filled the rock almost disappears. Where there were many forms, there are now few. Where large fossils were common, they are suddenly absent. This is not a slow decline stretched across thousands of years. The transition fits within a very narrow vertical space in the rock, often less than a meter, sometimes only centimeters. That vertical distance represents time, and that time is short. In geological terms, it is abrupt. Entire groups vanish at this level. Non-avian dinosaurs are one of the most well-known examples. Below the boundary, their remains appear on every continent. Many species, many body sizes, many ecological roles. Above the boundary, they do not appear again. There is no partial continuation, no reduced population lingering upward through the layers. They stop. The same pattern appears in the oceans. Ammonites, once abundant and diverse, disappear entirely. Their shells are common below the boundary, then absent above it. Marine reptiles vanish. Large predatory forms that dominated ancient seas are gone. Plankton communities change dramatically. Many species of foraminifera and calcareous nanoplankton disappear, replaced by smaller, simpler forms. Reef systems collapse. Complex coral structures do not continue uninterrupted through the boundary. The builders of those systems are reduced or eliminated. This loss is not selective in a comforting way. It does not only affect the large, it does not only affect the specialized. It cuts across environments, land, sea, freshwater. Organisms that lived in different climates, different regions, different ecological roles show the same pattern. Below the line, present. Above it, absent. What makes this especially striking is the timing. The disappearance happens at the same relative moment around the world. Sedimentary layers deposited in shallow seas show the change. Deep ocean sediments show it too. River floodplains, coastal margins, continental interiors. Different depositional environments record the same biological interruption. That synchronization matters. If extinction was driven by slow climate change or gradual sea level shifts, the losses would be staggered. Some regions would change earlier, others later. But that is not what the rocks show. They show compression, a narrowing of life into a smaller set of survivors. In many sections, the layers immediately above the boundary contain what scientists call disaster taxa, organisms that tolerate extreme conditions. Small body sizes, simple structures. broad environmental tolerance. They appear suddenly, not because they evolved at that moment, but because everything else is gone. It is not recovery yet, it is survival. The contrast between below and above is stark. Below the boundary, food webs are layered. Producers, consumers, predators. Energy moves through complex chains. Above it, those chains are broken. Plant fossils become sparse in some regions. Pollen records show a sharp drop in diversity. Fern spores become dominant in many places, suggesting a temporary simplification of vegetation. In the oceans, carbonate production drops. Fewer organisms are building shells. Sediment composition changes as biological input declines. This is not a quiet adjustment. It is a sudden reduction in biological complexity, and it is recorded without emotion. Stone does not exaggerate. It does not dramatize. It simply preserves absence. One of the most unsettling aspects of this boundary is how thin it is compared to what it represents. A few centimeters of rock, separating worlds. Below it, ecosystems that took tens of millions of years to assemble. Above it, a planet trying to function with far fewer pieces. The scale of loss becomes clear when you consider proportions. Estimates suggest that roughly 3/4 of all species on Earth disappeared at this boundary, not over a long era, not spread across ages, at once. Marine species were hit especially hard. Many groups lost more than half of their diversity. On land, large animals were disproportionately affected, but smaller organisms also suffered significant losses. Size did not guarantee survival, neither did habitat. Some lineages survived by chance, location, or tolerance. Many did not. The fossil record does not show panic. It does not show struggle. It shows discontinuity, a layer where familiar forms stop appearing, a layer above which evolution has to begin again, using fewer materials. This compression of loss is what gives the boundary its weight, not because it is dramatic in appearance, but because it is efficient. It removes complexity quickly, and it does so without warning in the record itself. There are no long signals in the layers below that predict what is coming. No gradual decline in diversity that prepares you for the absence above. Life is present, and then it is not. For scientists, this pattern raised a difficult question. What kind of event could cause such a sharp, synchronized biological collapse? One that affects oceans and continents at the same time. One that operates faster than evolutionary adaptation. One that leaves behind a thin chemical marker and a sudden silence in the fossil record. The boundary does not answer that question by itself, but it makes the question unavoidable. And to understand the cause, the next step is to look not at what vanished, but at what managed to remain. The boundary matters because it does not explain itself. It does not tell a story. It does not suggest motives or sequences. It simply marks a moment. In geology, that matters more than narrative. This layer is not important because it is dramatic to imagine. It is important because it is precise. It functions as a timestamp. A thin physical reference point that allows everything above and below it to be compared. When geologists examine rock layers, they look for continuity, gradual changes, transitions that stretch over thickness and distance. Most boundaries are diffuse. They fade into one another. One environment slowly replaces another. This one does not. The KT boundary is narrow, clean, reproducible. You can find it in a limestone cliff in Europe, in a sediment core pulled from the deep ocean, in ancient river deposits far from any coast, different environments, different deposition rates, different local conditions, the same line. That correlation is not assumed. It is measured. Chemical signatures align. Microfossil patterns align. Radiometric dates converge. When multiple independent records point to the same moment, confidence increases. This is why the boundary carries weight across disciplines. Paleontologists use it to compare biological change. Geochemists use it to trace material sources. Stratigraphers use it to align time across continents. It creates a shared reference. Without it, discussions of extinction would rely on regional patterns. One site showing loss here, another showing change later. With it, those patterns lock together. The boundary allows scientists to say that events recorded in different places happened at the same time. That simultaneity is critical. If extinction were driven by slow environmental drift, different ecosystems would respond at different rates. Tropical systems would shift differently than polar ones. Deep oceans would lag behind shallow seas. But the boundary shows compression. The losses appear clustered around the same narrow interval everywhere it is measured. That is not a story choice. It is a constraint imposed by the data. Another reason the boundary matters is its uniqueness. Earth's history contains many extinction events, some large, some gradual, some regionally intense. Most of them do not leave such a clear physical marker. They are inferred from patterns in fossils, from long-term declines, from changes spread across thick sequences of rock. The KT boundary stands apart because it combines biological change with a distinct chemical signal. The Iridium Spike is not subtle. It rises sharply above background levels, then falls just as sharply. It does not blend upward or downward. It does not appear repeatedly. It is confined. That confinement limits interpretation. You cannot stretch it over long durations without contradicting the measurements. This is why alternative explanations face difficulty. Volcanic activity can release trace elements. Climate change can stress ecosystems. Sea level shifts can alter habitats, but none of these processes produce a single globally synchronous chemical layer with such uniformity. They operate unevenly, they vary by region, they leave extended signatures. The boundary does not. It represents an interruption, a brief event recorded as a thin deposit followed immediately by altered biological conditions. This is why physical proof matters. Narratives can be compelling, hypotheses can sound plausible, but rocks do not respond to persuasion. They preserve what happened, not what seems reasonable. The boundary forces explanations to fit its constraints. Any proposed cause must explain several things at once. Why the chemical anomaly appears everywhere. Why it is confined to a narrow interval. Why biological losses align with it so closely. Why recovery above it is delayed and uneven. If a theory explains only one of these, it is incomplete. The boundary demands coherence. It also limits exaggeration. There is no room in the layer for prolonged catastrophe, no thickness to hide extended chaos. The record shows a sharp transition, followed by a long aftermath. That distinction matters. The event itself was fast. The consequences were long. The boundary marks the first, not the second. This separation helps prevent confusion between cause and effect. The extinction did not unfold slowly over millions of years. The disruption occurred quickly, and the biosphere spent a long time responding to it. The boundary is the dividing line between those two phases. Because it is physical, it can be revisited. Samples can be reanalyzed with new techniques. Measurements can be refined. New locations can be added. The boundary does not depend on interpretation alone. It exists whether or not a particular theory is favored. That permanence gives it authority. When scientists disagree about causes, they still agree on the boundary's presence. That shared ground matters. It keeps discussion anchored. The boundary also matters because it simplifies complexity without erasing it. Earth systems are complicated. Biology, chemistry, physics, and geology interact in overlapping ways. The boundary does not reduce that complexity, but it organizes it. It provides a fixed point around which complexity can be studied. Below it, one set of conditions. Above it, another. The difference is not philosophical, it is measurable. This is why the boundary is taught not as a story, but as evidence. Students learn where it appears, what it contains, what changes across it. Only after that do they learn interpretations. That order matters. Evidence first, narrative second. The boundary encourages restraint. It prevents overextension. It discourages vague explanations. It asks a simple question again and again. What happened here? And because the question is tied to a physical layer, answers must stay grounded. As analytical tools improve, the boundary continues to be examined at finer scales, particle sizes, isotope ratios, microfossil turnover measured layer by layer. The more closely it is studied, the more its sharpness stands out. That sharpness is not theatrical, it is exact, and it is that exactness that gives the boundary its importance. Not because it tells us how to feel about the past, but because it tells us when something ended and something else began. It prepares the ground for interpretation without dictating it, and it ensures that whatever story is told next must answer to stone. 3.3. Eliminating alternatives. To understand what happened, scientists first had to understand what did not. That process took time, not because alternatives were ignored, but because they were tested carefully, one by one, against the same physical record. Gradual climate change was an early candidate. Earth's climate has shifted many times before. Ice ages advanced and retreated. Temperatures rose and fell. Ecosystems adapted, migrated, or collapsed slowly. Those changes leave signatures. They appear as extended trends. Fossil diversity declines over long intervals. Species disappear unevenly. Some regions are affected earlier, others later. That is not what appears at the boundary. The fossil record below the line is diverse and stable. Immediately above it, diversity drops sharply. There is no long tapering, no drawn-out decline stretching across layers. The compression in time is too tight. Gradual climate change cannot produce a global biological shift that aligns so closely with a single thin sediment layer. Climate operates continuously. The boundary records an interruption. Volcanism was another serious candidate. Large volcanic provinces have reshaped Earth before. They release gases. They alter atmospheric chemistry. They can stress ecosystems over long periods. Volcanic ash layers are common in the geological record, but ash behaves differently. It is usually thick near its source and thins with distance. Its chemical composition reflects local geology. Its distribution is uneven. The boundary layer does not follow that pattern. The iridium concentrations are similar across distant locations. Not identical, but consistent within a narrow range. Volcanoes also struggle to explain the timing. Volcanic episodes span thousands to millions of years. Even intense phases are extended. The boundary does not show repeated pulses, it shows one peak, and that peak aligns with extinction patterns across marine and terrestrial systems. Volcanism alone does not explain that simultaneity. Some hypotheses combined causes: volcanism weakening ecosystems, climate stress accumulating, then collapse. But this raises another problem. If systems were already failing gradually, the fossil record would show staggered losses. Some groups would decline earlier, others later. Instead, many unrelated organisms disappear at the same stratigraphic level. Marine plankton, large land animals, shallow water species, and open ocean species. These groups do not share habitats. They do not respond to stress in the same way. Yet their disappearance aligns. That alignment demands an explanation that operates globally and quickly. Another challenge for gradual explanations is the chemical signal itself. Iridium is not produced in large quantities at Earth's surface. It is rare in crustal rocks. It does not concentrate naturally in sediments without a specific source. To explain the observed spike, any hypothesis must account for both the amount and the distribution of iridium. Climate change does not move iridium. Biological collapse does not create it. Volcanism can release trace amounts, but not at the observed scale without leaving other, stronger volcanic signatures. Those signatures are absent or insufficient. What remains is the requirement of simultaneity. The boundary appears at the same relative time across the planet, not approximately, not within broad margins. Within geological resolution, it is synchronous. That fact alone eliminates many gradual processes. Earth systems usually respond locally first, then globally. Oceans respond differently than continents. Tropics respond differently than poles. Here, the response is immediate and shared. The convergence of evidence is what strengthens the conclusion. No single observation is decisive by itself. The Iridium Spike alone would raise questions. The fossil losses alone would suggest extinction. The thin boundary alone would mark a transition. Together, they constrain explanation. Each line of evidence supports the others. Chemical data points to an external source. Stratigraphy points to a brief event. Biology points to abrupt disruption. Remove one, and uncertainty grows. With all three aligned, alternatives narrow sharply. This is not about preference, it is about compatibility. Any explanation must fit all observations simultaneously. Gradual climate change fails the timing. Volcanism fails the chemistry and distribution. Regional disasters fail the global reach. The remaining explanation must operate fast, distribute material worldwide, and deliver energy sufficient to disrupt ecosystems across all environments. The boundary does not demand belief. It demands consistency. This is why scientific consensus formed slowly. Not because evidence was weak, but because standards were high. Each alternative was examined, tested, and compared to the same physical layer, and each fell short. What remains is not a dramatic conclusion, but a constrained one. The boundary does not tell us what to imagine. It tells us what must be true. Something happened quickly. Something affected the entire planet. Something left a chemical trace that still exists. And whatever that event was, it reshaped life so thoroughly that Earth's biological history had to begin again above a thin line of dust. The record allows no softer explanation. It is quiet, it is precise, and it is uncompromising. What comes next is not speculation. It is reconstruction, guided by what the boundary permits and by what it refuses to allow. The surface of the planet does not forget because it does not need to remember. It simply accumulates, layer by layer. Material settles. Some of it is disturbed, some of it is removed, but much of it remains where it fell, pressed slowly into stone. This process does not depend on attention. It does not require observation. It happens whether anything is watching or not. Rocks form as long-term storage of events because they are stable over time. Once sediments are buried and compacted, they change very slowly. Chemical bonds lock in compositions. Structures resist rearrangement. This is why ancient events can still be examined. The KT boundary is one example of that stability. For more than 60 million years, continents moved, oceans opened and closed, mountain ranges rose and eroded. Life diversified again, filling empty ecological space. Through all of that, the boundary remained intact. It was compressed under kilometers of additional sediment in some places. In others, it was uplifted and exposed by tectonic forces. Still, its position relative to surrounding layers did not change. It stayed where it formed. That persistence matters. If the boundary were easily erased, its usefulness would be limited. It would appear only in protected environments or isolated locations. Instead, it appears across a wide range of geological settings: shallow marine deposits, deep ocean sediments, river floodplains, coastal shelves. Each environment has different dynamics, different rates of deposition, different levels of disturbance, yet the boundary persists in all of them. This tells us something important about the conditions that followed its formation. The layer was not heavily reworked. It was not mixed deeply into surrounding sediments. The lack of extensive biological activity immediately after the event reduced disruption. Later, as ecosystems recovered, the boundary had already been buried. Once sealed, it became part of the crust. From that point forward, it was no longer exposed to surface processes. Weathering effects exposed rock, erosion removes material, but buried layers are protected. They exist independent of climate, independent of life. This independence is why physical records carry weight. They are not influenced by interpretation. They do not adjust to expectation. A fossil assemblage can be incomplete. A chemical measurement can be refined, but the layer itself does not move to match theory. It remains available for re-examination. Over time, analytical methods improve. Early studies measured elemental concentrations at coarse scales. Later, work refined particle sizes. Isotopic ratios were added. Microfossils were counted in thinner slices. Each generation of analysis returned to the same boundary. The results converged, not because earlier interpretations were repeated, but because the physical evidence remained consistent. That consistency is rare in Earth history. Many ancient events are inferred indirectly. Their timing is approximate, their causes debated. The KT boundary is different. It provides a fixed reference that does not depend on continuous fossil presence or regional preservation. It exists even where fossils are scarce. It exists even where ecosystems were simple. This allows correlation without assumption. A sample taken from one continent can be matched to another based on the same chemical signature. That matching does not require knowing what lived there. It requires only recognizing the layer. In this way, the surface of the planet stores information without interpretation. Humans did not place this layer. They did not label it. They did not preserve it intentionally. It existed long before it was noticed, and it would continue to exist even if it were never studied again. This permanence changes how catastrophe is understood. The impact itself was brief. The biological consequences unfolded over time. But the physical trace of the event remained constant. That constancy allows continuity to be studied alongside disruption. Above the boundary, life returns. Slowly at first, then diversifying. New species appear, new ecosystems form. New dominant groups rise. All of that change rests on top of a stable physical reference. The boundary does not interrupt the record permanently, it divides it. Below, one configuration of life, above, another. Between them, a thin layer that does not participate in biology at all. It is inert, it is passive, and because of that, it is reliable. This is how planetary processes preserve information across deep time, not by intention, not by design, by accumulation and stability. The same mechanisms that allow mountain ranges to persist also allow thin chemical layers to survive. Pressure lithifies, burial protects. Time slows change. From a human perspective, this feels like memory, but it is simply physics operating over long durations. The boundary's survival does not imply awareness. It implies resistance to alteration. That resistance is what makes reconstruction possible. It allows scientists to move forward in the record without losing the point of reference behind them. The catastrophe does not erase continuity. It becomes part of it. The planet did not reset. It carried on. And the boundary remained, marking where conditions changed, while allowing everything afterward to accumulate normally. What follows is not chaos without structure. It is recovery built upon a preserved foundation. Life reorganizes above the line. Sediments continue to settle. Time resumes its layering. The archive remains open, not frozen, not finished, just continuing, with one thin layer quietly holding its place as everything else moves forward. The boundary is still here. It has not faded, it has not dissolved, it has not been replaced. It lies beneath forests whose roots never reach it, beneath cities whose foundations stop far above it, beneath oceans whose floors are layered with sediments that arrived long after. It exists under places where people live, work, sleep, and move through their days. Most of the time, it is tens to hundreds of meters below the surface. In some regions, much deeper. In others, closer, exposed only where erosion or excavation has revealed it. But even when it is close, it remains unnoticed. There are no surface signs, no changes in soil color that stand out, no visible markers in the landscape. Daily life passes above it without interruption. Roads cross over it, rivers flow above it. Buildings rise and fall without ever touching it. The layer does not announce itself. It does not require attention to persist. Its composition has not changed in any meaningful way since it formed. The iridium concentration remains. The fine-grained material remains. The boundary remains thin. Pressure has compacted it. Burial has protected it. But its identity is intact. This persistence is what allows it to exist beneath the present world without interfering with it. It does not affect weather. It does not influence ecosystems today. It does not shape human history directly. It simply remains. Above the boundary, life continued. Not immediately, not quickly, but steadily. The fossil record above the layer shows recovery that unfolds over millions of years. Early ecosystems are simpler, species are smaller, diversity is reduced. Then, gradually, complexity returns. Plants spread again, insects diversify, marine ecosystems rebuild food webs, new dominant species appear, unrelated to those that vanished. Mammals expand into niches that were once occupied by other groups. Birds diversify from surviving lineages. Reptiles persist in altered roles. None of this happens abruptly. Recovery is uneven. Some environments stabilize faster than others. Oceans respond differently than land. Tropical regions recover differently than temperate ones. But the direction is consistent. Life resumes. Above the boundary, sedimentation continues as well. Rivers deposit sand and silt. Seas lay down carbonates. Volcanic ash settles in thin layers, later altered and mixed. Time resumes its usual pace. The boundary does not repeat. It remains a single marker, followed by continuous accumulation. This distinction matters. The collapse was confined to a moment. The continuity extends far beyond it. The planet does not remain locked in disruption. It absorbs the change and moves forward. From the perspective of deep time, the boundary becomes one layer among many. Important, distinct, but not isolating. Human life exists far above this layer, not just physically, but temporally. 66 million years of sediment, erosion, and biological activity separate the present from that event. Entire lineages rise and fall within that interval. Human history occupies only the uppermost fraction of the geological column, a thin surface layer compared to what lies beneath. There are no signals in daily surroundings that point to the boundary below. No vibrations, no emissions, no reminders. Its presence does not change the sound of the wind or the movement of water. It does not influence seasons. The ground feels solid regardless of what lies deeper. This absence of warning is part of what defines geological time. Major events leave records, not signals. They are preserved quietly, accessed only through deliberate examination. The boundary does not communicate urgency. It does not suggest threat. It exists as information, not instruction. Earth functions as a system that accumulates outcomes. Processes operate, materials move, layers form. The system does not react to meaning. It responds to physics, chemistry, and biology. Records are produced as a result, not as a goal. The boundary is one such record. It does not tell us what should have happened. It does not express loss or recovery. It simply preserves a transition. From one state to another, human awareness enters much later. When the layer is studied, it becomes part of understanding. When it is ignored, it remains unchanged. Its existence does not depend on recognition. That distance can feel unsettling, but it is also stabilizing. The planet does not require constant attention to function. It does not signal every past disruption through surface features. Most of what has occurred is buried, layered, and silent. This allows the present to exist without constant reference to the past. Forests grow without knowing what lies below. Animals move across terrain shaped by long processes they do not sense. People build on surfaces formed by events far outside human timescales. The boundary does not intrude, it coexists. And because of that, it invites a particular kind of awareness, not alarm, not anticipation, recognition. Recognition that the surface is only a thin slice of a much longer sequence. Recognition that stability can exist above records of collapse. Recognition that continuity does not require forgetting. The present moment is supported by layers that hold outcomes without emotion. The ground is solid, the air is clear, life continues. The boundary remains beneath it all, unchanged, unobtrusive, complete. And knowing that does not demand action. It allows idleness, a return to the present, grounded in the understanding that the world carries its history quietly and continues forward without needing to announce it. Nothing is required now. there is only the surface beneath you, the time above it, and the calm persistence of layers holding what once happened while everything else rests.